Okay, time is ticking. You may already start your sharing your screen and presenting your first milestone of the project.
Hello.
Yes, we can hear you.
Okay. Good afternoon, Sir Dedi and Kak Devita, also friends. Today we're going to present our plan for our final project. Our final project is thermal regulation in an active temperature sensor. Introduction. Thermistor. It is also known as thermoresistor, and thermistor are a type of semiconductor, meaning they have a greater resistance than conducting materials, but lower resistance than insulating materials. The relationship between a thermistor's temperature and its resistance is highly dependent upon the materials from which it's composed. The manufacturer The manufacturer typically determines this property with a high degree of accuracy, as this is the primary characteristic of interest to a thermistor buyer. Next one is types of thermistor. There are two types of thermistor. The first one is NTC or negative temperature coefficient, and the second one is PTC or positive temperature coefficient thermistors. The first one is NTC thermistor. NTC thermistor is inversely proportional to temperature and resistance. So if the thermistor resistance value drop, then the temperature around the thermistor is high. And when the temperature decreases, the electrical resistance value will increase. The second one is PTC thermistor. The relationship between temperature and resistance in this PTC thermistor is directly proportional. It means when the temperature increases, the value of the electrical resistance also increase, and also the other way around. And then this is the graph for temperature versus resistance for PTC and NTC, and this is the symbol for both of them. NTC and PTC thermistors are electronic components that function as sensors in electronic circuit related to temperature. The second one is thermistor operating temperature, varies depending on the thermistor manufacturer. Generally, the temperature range from -90 degrees Celsius to 130 degrees Celsius. NTC and PTC thermistor are an electronic component classified as a transducer component. This is the use of thermistor. We can use it as digital thermometer, PCR, fire detectors, electric ovens, microwave, refrigerator, sensors to monitor battery pack temperature in cell phone and laptop when charging, sensors to monitor incubator temperatures, and it is also used as a component in measuring the thermal conductivity of electrical materials. Example, maintaining resistance in order to compensate for the effects caused by temperature changes on the circuit.
For finding the temperature, we are going to use two equations as our tool. The first one is Steinhart equation. The equation is shown in the slide, where A, B, and C is the Steinhart coefficient. In order to achieve A, B, and C, we are going to test the thermistor with 3 different temperatures. And then we will get 3 different resistance of the thermistor. And then after we get the 3 linear equation, we can solve ABC using the help of mathematical tools such as Octave. Next. The second equation that we are using is the standard equation for an NTC thermistor resistance. The equation is shown in the slide. Beta is obtained from the NTC datasheet. The beta is constant and each NTC has a different value of beta. For now, our beta cannot be obtained because we are still discussing what NTC are we going to use. What type of NTC are we going to use? Next. Wait. How it works, we are going to find ABC coefficient in Steinhart equation, and then we will test that equation to the standard equation. if both equation arrives at the same result, the accuracy of the equation and device is good. Example, we find the Steinhardt equation 1/t is equal to 2 plus 3 ln r plus 4 ln r cubed. And now we will test it using 50K resistance, and then we will calculate the T. After we get the T and resistance, we are going to insert the R and T to the standard equation using the beta from the data sheet. If it is the same, and then it is correct. Next.
So this is the essential considerations when selecting NTC thermistor. The first one is temperature range. The second one is accuracy. Third one, stability. Fourth one, packaging. And the last one is noise immunity. As for the equipment that we're going to use these equipments, as you can see in this slide. Next.
For the concept, the circuit consists of a resistor and a thermistor. Resistor has a fixed value of resistance, while thermistor has a changing value of resistance according to the temperature. Changing of thermistor's resistance and stability of the resistor's resistance yield to the changing of voltage distribution. So by using these changes in voltage distribution, the resistance of the thermistor can be calculated because the voltage source is fixed, which is 5 volt, and the resistor's resistance is fixed. The voltage between the thermistor and resistor is measured, and then the voltage of the resistor can be obtained by using this following equation. V resistor over Z thermistor is equal to V thermistor over Z thermistor. V thermistor is 5 minus V resistor. And then by doing mathematical operation, we will get the equation for Z thermistor. Next. For the procedure, first of all, we are going to test our resistor using circuit in figure 1. We will measure the current, and then we will calculate the resistance. We do this because the resistor in the market is not ideal. There is some tolerance, so we have to get the exact value of resistance first. And then we will build the figure based on figure number 2. And then, oh yeah, for figure number 2, this is actually a thermistor, but in Tinkercad, we don't have thermistor. So just make resistor as thermistor. And then the code will be made. The algorithm of the codes are A. The Arduino will get the voltage difference of the wire between the thermistor and resistor as an analog input. And then the code consisting of calculation by using voltage divider principle will be done to find the resistance value of the thermistor. C. The code will use the resistance value to calculate the temperature by using Steinhardt equation. D. The value of the temperature will be shown via LCD screen. Next.
And this is the additional explanation for our project. Okay, so for the first one, the length of the cables, the red and the yellow one, as you can see it here, the red and the yellow one, is relatively long so that the position of the thermistor and the resistor is wide. We do this with the intention that the outside temperature does not affect the resistor. The second one, the resistor will be coated with the heat insulator so that the resistor is protected from outside temperature. And the last one, technical specification of the thermistor that we're going to use. The first one is resistant at 25 degrees Celsius. The beta value is around this one, and dissipation factor around this. Thermal cooling time constant, then this one, and the thermistor temperature range from minus 55 degrees Celsius to 125 degrees Celsius. That's all from us. Thank you for listening and have a nice day.
Hey, thank you, group, for the on-time presentation. So I would like to ask question, group 2, Catherine and Elisa, to ask questions for the presenting group. Catherine and Elisa, please turn on your videos and ask questions.
Group 4, right?
Yes, group 4.
I heard that you mentioned, wait, let me see my notes. Transducer.
Yes.
What is transducer? I don't. I'm confused about that one.
Oh, so transducer is a device that can convert one energy to another. So for example, it can convert heat energy into electrical resistance.
That sounds quite clear. Thank you, I guess.
That's all.
Yeah.
Catherine does not want to ask.
Why thermistor serve as a good temperature reading tool?
Actually, thermistor is good because the temperature coefficient of the thermistor is like very good compared to the other metals. Maybe it is 10 until 100 times better than the ordinary metal conductor. That's why it is good for heat conductor.
Okay, thank you.
Okay, thank you, Catherine. Kak Devita.
Can you hear my voice, guys? Or maybe I will put up my mascara first. Hello, check. Can you hear
Yes.
me?
We can hear you.
Okay. Well, it is good. It's a good and very good. It's a very good presentation, yeah. But I got. I see a lot of typo here. It means that you manually type all the materials into your presentation slide, yeah. Yeah, good. Maybe I don't have questions. I just want to suggest. I just want to give you some suggestion. Maybe. Mm, I think for next milestone, it is better to you to make the flow chart, yeah, for the programming code
Yeah,
for the
agree.
Arduino, yeah, yeah, for all the groups, yeah, not only for group 4. And then you can also put the block diagram into your presentation slide. Okay, I think what else? I think that's all from me, Aditi.
Okay, thank you, Kak Devita. Please, group 4, pay attention and take note of the points that Kak Devita mentioned. Okay, my question now. Are you ready?
Yes.
The most difficult question of all.
Yeah, it's okay.
Okay, don't be scared. Yeah. I think you misunderstand your project. So what you are presenting is passive thermal sensing. What I ask for project 2 is active temperature sensing. Did you or did you not watch the video again of my presentation, of the explanation?
Yes, I watch it.
Good.
Why we do this thing? Because Arduino cannot read current, while in your video there is a change in current that we need to see.
Yeah, this is the purpose that you have electric circuit analysis course to change current into voltage. Yeah, not everything is already ready for you just to eat. You have to cook, guys. You are going to be engineers. Yeah, it means in the terms of hotel tourism, we teach you to be cook, to be chef, not just directly eating the food. Cook it. You have to use your ingenuity, find information, how to make current to voltage converter. So I don't see any heater being used in this your presentation. While for active temperature sensing, you have to use heater. A heater, so you have to put voltage or current, whatever, and based on that, the change of the resistance, then the flow will be changed, and then using a feedback mechanism to regulate the voltage or current such that then the heating will stay the same at that element, and this is based on null, null measurement. So the amount of the voltage or current used to adjust the heating is proportional to the temperature increase or decrease. Yeah, I'm sorry. So for the content wise, your mark for now is low. Presentation wise is okay, good. Yeah, you can answer question maybe, but this is not the project that I wanted to do. This is too easy. High school students can do it. Sorry to say. Yeah. Okay, group 4. That's why. Thank you. Please revise and do better for the next milestone.
Okay.
Okay, thank you,
Thank you.
sir.
So next group, next presenting group will be group 2, Catherine and Elisa. Catherine and Elisa, turn on again your video. Mana Catherine? Okay, you may start your group. This is group 2, yeah. Group 2 is doing first project, thermal regulation in PCR check. Okay, you may start anytime you're ready.
Okay. Wait, I share screen. Can you see my screen? Hello?
Yeah.
Okay.
Yes, I can see.
Okay.
So, good afternoon, everyone. Today, me and Elisa will explain about thermal regulation in a PCR chamber.
So first up, we are going to tell a bit of theory about PCR, which stands for polymerase chain reaction. This method is used to make millions and sometimes even billions of specific DNA. Like for example, perhaps an STR sample in a fast time so rapidly. This method is also developed in the 1890s, precisely 1985 by Carrie B. Mullis. This fast and relatively inexpensive technique sometimes could also be called molecular photocopying. And once amplified, the DNA produced by PCR can be used in many different laboratory procedures. Uh, what we stated here is for mapping techniques in the HGP, Human Genome Project. And also, PCR is very valuable in a number of laboratory and clinical techniques, for example, such as DNA fingerprinting, detection of bacteria or viruses, particularly AIDS, and also diagnosis of genetic disorder. Um, This is basically the steps of PCR, as you can see, where where first we only have this one DNA, and then after several steps, we will end up with millions and millions of copies. The steps will be explained by Catherine.
So, the first step in PCR is initialization, which is the required require a heat activated by hot start PCR. It consists heating the reaction chamber to a temperature of 94 until 96 Celsius or 98 Celsius extremely thermostable polymers are used, which is then held for 1 until 10 minutes. Second is denaturation. This step is the first regular recycling event and consists of heating the reaction chamber to 95 until 98 Celsius or 20 until 30 seconds. Discuss DNA melting and or denaturation of the double-stranded DNA template by breaking the hydrogen bonds between complementary bases, yielding to single-strand DNA molecules. Third step is annealing. In the next step, the reaction temperature is lowered to 50 until 65 Celsius for 20 until 40 seconds, allowing annealing of the primers to each of the single-strand DNA templates. The fourth step is extension. The temperature at this step is dependent on the DNA polymer used. The optimum activity temperature for thermostable DNA is approximately 75 until 80 Celsius. Top temperature of 72 Celsius is commonly used with the enzyme. Next step is final elimination. This single step is optional, but is performed at a temperature of 70 until 74 Celsius for 5 until 15 minutes after the last PCR cycle to ensure that on any remaining single-strand DNA is fully eliminated. The last is final hold. The final step cools the reaction chamber to 4 until 15 Celsius for an indefinite time and may be employed for the short-term storage of the PCR products.
Next up is the system plans. Now, for our plan, we are planning to use these things that you can the list on the PPT for our equipments. So far, we have decided on Arduino heater, wire, temperature sensor, LCD filter, cooling, and breadboard. And this is the schematic of circuit that we have created. Although this is still a rough sketch. Now, as you can see here, we have an Arduino with 5 volt that we chose. This Arduino, then we connected to a breadboard. Then we also connected an LCD monitor to the breadboard as well, so that we can monitor the temperature when we are starting the system. As you also can see, we attach a heater system to the breadboard as well. The heater system will basically what it said, it will heat up the PCR chamber. We also added a temperature sensor so we can monitor at what temperature the system is at an exact, yeah. Oh, okay, we also add in a peltier cooler so that we added a peltier cooling to the breadboard so that we can control the heat of the chamber to which we desire. And then all of these 3 components we then connected to the PCR chamber directly, as you can see. This is basically the rough sketch of our schematic circuit.
So this is a system flow diagram that contain our concept. So the step is start, which will initialize the heating system, and then the system is heat until the temperature of 95 degrees Celsius is achieved. So when the temperature reaches 95 degrees, the cooler will turn on and the heater will be turned off after 10 seconds. These cooler are used to trigger on to maintain the temperature. So the heater is off and then the cooler is on. So basically the temperature will drop and will drop to 65 degrees Celsius. So when the temperature is 65, we turn the heater on and we turn the cooler off after 10 seconds. And then the temperature will increase because the heater is on. And when the temperature is reached 72 Celsius, the cooler will turn on after for 10 seconds and then turn off. And the heater will still turn on, which is it will back to the initialization and wait until it reaches 95 degrees. So that's basically the system flow diagram that we want to make. Okay. Thank you.
Okay, thank you for group 2, yeah, for the presentation. So I would like to request group 4, Nikki and Michelle, to ask questions. So please, Nikki and Michelle, turn on your video and ask some questions for Elisa and Catherine. Please unmute yourself, yes.
Hello?
Yes, we can hear you.
Okay. Before you have mentioned Peltier cooler, right?
Yes.
Yeah, what is that?
Peltier core is a solid state active heat pump which transfers heat from one side of the device to the other with consumption of electrical energy. This is depending on the direction of the current.
Okay, thank you.
You're welcome.
How does the Peltier cooler work?
Can I answer?
Yes, yes.
Okay. So the Peltier cooler system basically heat pump. Sorry, no, not heat pump. So in a Peltier cooler, solid state active heat pump. This solid state active heat pump will which transfers heat from one side of the device to the other side of the device, and then with consumption of electrical energy depending on the current given. More or less like that.
Okay, that's it.
Sorry, transporting what from other side to other side?
Wait. I think I answered wrong. Can I, fix my answer?
Yeah.
I think I okay, wait. So in a Peltier cooler, we apply volt across the joint conductors in the circuit to create basically an electric current. So when the current flows through the junction of two conductors, heat is removed at one junction and cooling occurs. So heat is deposited at the other junction. So the main application of the pelleter effect is cooling. I know it doesn't really make sense. So,
Okay, thank you.
Okay, Kak Devita, maybe one short question. Kak Devita, please unmute yourself.
Sorry, I forgot. Thank you. Okay, you already explained about the cycles of PCR, right? So how you make the heater temperature is stable in a certain point?
How to maintain the temperature? Or
You make it stable.
yeah. By turn the capital color on, I think, because one side is heating and one side is cooling. So basically, I think it will make the temperature stable. But I don't know yet. Not sure. We
yeah,
haven't tried that.
we actually are very confused about that as well. We were discussing about that as well, about how we can maintain the heat for a certain
Yes.
amount of time.
So do you have a plan to make it stable?
I'm sorry. Please.
Do you have
Yeah,
plan how to build the heater, how to build your instrument so that it can stable for a certain point in a certain time? Or maybe you have another instrument,
I think I will turn off the heater.
turn off and turn on.
Turn on and then turn it off. I mean,
basically like this.
So how to make it turn it on and turn it off? Did you do that manually by turn off and turn on the software? Or
perhaps we can add another component which will perhaps act as the brain, where we will put a code that where when the temperature already reached 95, we will command it to turn off the heater and then turn on the cooler and such for when the temperature reached 65 and then 72.
I think we gonna try to make it automatically, but if it is fail, I think we consider to make it manually.
Yes. We try both
guys,
ways.
you cannot do it manually. You see any PCR machine which is operated manually, 95, 60, 65 heater turn on, until
yeah, if it is fail.
The purpose of this project is for you to make that automatically. So like it or not, you have to find, to read, to look for some control mechanism at the internet, whatever. Yeah, you can use as simple as on-off control system. We call it on-off system.
Sir.
And otherwise, if you want to use more advanced control algorithm, you can use PID, PI, PD, whatever. But maybe you haven't got the course yet. But it doesn't matter. This is experiment. You can search now. You have the internet as your library, so you can find the best control algorithm to maintain the temperature at certain time, at a certain duration.
PID,
PD, PI, proportional integral derivative control algorithm. That is a bit advanced, yeah, but it should be made possible using the Arduino. With Arduino, you can program it by software.
So we didn't need the PID and something. So we just need
on Arduino. That is why we gave you Arduino.
Yes.
By the way, Kak Devita, the Arduino is already sent, right? All the package.
It's still in the Kak Stasia's home.
Okay.
I send the package.
Can you please send them, because they are complaining already yesterday.
As soon as possible.
Yeah, they
Sir,
want to try immediately to program the Arduino because
Yeah.
not much time, already week 12 now.
itu dikirimnya tuh ke setiap anak atau ke tiap grup?
Yeah.
Students.
Every student, every
Oh,
single
students.
student.
So every
So-
student must make it by individuals. I mean,
Yes, you may make it individual, but you collaborate to have the same solution, yeah, so that everyone can try at home, at each their home. Oh enggak, so Catherine you can try in Surabaya, Elisa can try in Batam
okay.
individually, but you can collaborate. You can have Zoom together or Google Meet together. Oh
Yeah,
yeah, let's
discuss it
connect it
together.
with them.
Sir, quick question. Do we need to document when we work when we try to build the circuit together
Yeah, of course.
for documentation?
You
Of
have to,
course, yes.
yes, you have to document everything.
Like when you do the lab, also you document the work. Okay, group 2, thank you very much. So please
Okay, thank
take
you.
notes, yeah, of the feedback from Kak Devita, from myself, from learn more, study more. Yeah, I know it is a forced learning. The project is a forced learning, not through a course, not a conventional course. You have to find your own information. Okay, I would like to
Thank
call
you.
then the next
Thank
group.
you, sir.
Thank you. The next group will be group 5, Osama and Martin. Okay, Osama and Martin, please, you may turn on your videos. Okay, already. Martin, where is Martin? And you may start whenever you are ready.
I'll present my screen first.
So group 5 is doing project number 2, yeah, thermal regulation in an active temperature sensor.
Okay.
Okay, good afternoon, everyone. Today, Martin and I are going to present our project of the thermal regulation in active temperature sensor. Before I go deep, let's see the temperature controlling device nowadays and how much it costs. There are numerous devices on the market that treat and monitor temperature from simple thermometer to black radiation optical measurement. And many clever designers have invented techniques ranging from simple to complex and obscure. And we are going to cover common and simple techniques of measuring using standard low-cost diodes. And that's what we are going to focus in our project. In the medical industry, the costing of the temperature controlling device is a bit high, and using low-cost diodes may be efficient and accurate like what we did in our project.
So first, we will mention what is the heater that we will use. We will use a simple copper wire made into like this one and connected to the power source. Because it is short-circuited, then it will get hot. And then the next one is the thermometer, or how we are going to measure the temperature. There are many types of thermometer. There's a superconductor, metal, and semiconductor. We will use semiconductor because it is the most accurate. And in semiconductor, there is two, thermistor and semiconductor diode. We can use, for example, silicon semiconductor diodes to measure temperature, and we can also use thermistor to measure the temperature. So this is the difference of using RTD or metal and semiconductor. So semiconductor have a faster response, and the temperature range is from minus 55 to plus minus 114. And then the characteristic of the graph is nonlinear, which is wait, what is that? I forget the name. Steinhardt equation. So this one is Steinhardt equation. And then the sensitivity of semiconductor diodes is high. So it's better for us to use semiconductor diodes. So I actually have tried to use resistor, which is also semiconductor, to measure temperature. And this is the graph of resistance versus the temperature. And we can use this result and put it into a Steinhardt equation to predict the temperature at which resistance.
Okay, so one of our components that we have used is a transistor. Transistor is a semiconductor device for amplifying and controlling and generating electrical signals. We use the transistor actually in our circuits to regulate the current, and we use Darlington transistor TIP120 specifically because the power source is high and because it works as a switch with Arduino because it's currently it can range from 0 to high ranges easily. The Darlington transistor is actually two bipolar transistor connected in such way that the current amplified by the first transistor and is amplified even further by the second transistor. This model offers high common emitter current again than if both we use separate transistor and can even take up less space because both transistors can share one collector. We tried actually to use a relay too. A relay is an electrically operated switch. It consists of the set of input terminals for a signal or multiply control signals. Before I forgot, actually, and Martin passed to another slide. We used 1 kilo ohm resistor between the Arduino pins and the resistor tip 120 base pin to ensure against the electrical shorts. The Darlington tip 120 may handle, as what I've understood, 60 volt and 5 ampere, but I don't think that the Arduino will do.
Okay, proposed design. So this part is the heater and this part is the switch of the heater, and the thermistor will calculate the heat, and when the temperature is higher, current temperature is higher than the target temperature, the heater will go off. But if the temperature is lower than the lower target, then the heater will go on. I think that's it.
Okay, so would like to ask group 3, Dev and Dimas, to ask question to Osama and Martin. So Dev and Dimas, please turn on your videos and ask questions.
Okay, I have a question. So, why do you use a transistor instead of the relay in the project?
Okay. You mean why do we use a transistor instead of a relay, right?
Yes, I think in two previous slides before this.
Yeah. Slide 8. No, the previous one. Okay. Relay is actually mechanical, but the transistor is auto. So the transistor can have more than two values rather than the relay. Relay only have two values, which is on and off. But the transistor can go to the high ranges, like what I've said, from 0 to high ranges. You think?
Yeah, thank you.
Okay, that's all. Group 5, group 3.
Oh, wait, I have a question, sir.
Yeah.
Will you use LCD screen in the circuit to show the current temperature?
Yeah, I think so. Yeah, in the future milestone, maybe we'll use LCD circuit so that we can monitor the current temperature, the temperature at the moment easily.
Okay. Kadevita, maybe some questions?
Maybe just short question. Why did you use LM35 as a temperature sensor?
Because it works at minus 55 to 125 degree.
Yeah,
You
why?
please so again the graph, the systematic graph, all of the graph, not only this part, where
This
the
one?
LM35 is also shown.
Oh, this one. So the thermistor will measure the heater, the heat.
Yeah, it means that the LM should touch the heater, right? Because the LM35 is, not like infrared or
Yes, they will
other
touch.
sensor. Yeah. Did you try to, replace it with IR sensor maybe? Or
Oh, did we try to use other temperature measuring device? I actually do this experiment to try another device to measure the temperature. And so far what I have is only resistor. So this experiment can only be done to resistor, but maybe in the future project, I can use it to measure the temperature with other things.
Okay, Kadevita. Yeah, I have one question there. So again, yeah, this is not active temperature sensing.
Yes, sir.
You know, well,
I just know.
yeah, just know why. So you didn't see you didn't watch again the video. That my explanation video. I put it on the Google Classroom. Did you watch it again or not?
I watch it again, sir. That's why I use heater, sir.
Yeah. Still, if you use heater, what you are doing now is what your design is not an active temperature sensing.
Passive.
Yeah, it is still a passive, right? Right.
Yes.
And what we want you to make is an active temperature sensing. Do you know what to change?
We don't use the thermistor, and then we directly control the current going into the heater.
Yeah, you are smart. Yeah, you understand. Okay, so you based on the current changes, yeah, because let's say when you touch the heater, for example, then the what do you call it, you introduce your temperature of your body, right? Then due to the temperature, the resistivity of the heater will change.
Yes.
So current will change as well. Then you use your Arduino to control the flow to maintain constant current, for example. Yeah, and that adjustment current will represent the temperature of your hand that is touching that heater. You get it, yeah? The idea.
Yes.
Okay. So you are similar misunderstanding like the first presenting group. Okay. So please change this. Yeah. So it means then currently from the content point of view, the mark is still low for your group, similar to the first presenting group. But good presentation and I think good ability to answer the question. Yeah. Thank you, group how many? Group 5. Okay, thank you very much, Osama and Martin. So
yes, sir.
Let's have a break for